In this problem, we have a piece of clay that's traveling to the right at a velocity v that impacts block 1. Block 1 is then compressed a distance x through a spring because the other side of the spring is connected to block 2, but it's held in place by a stopper. So we need to find the distance x that it's compressed. So this starts off as a momentum problem, conservation of momentum problem because of the collision. So I'm going to define the positive direction to be to the right. That's done. Then I'm going to make a statement of conservation of momentum. The initial momentum is equal to the final momentum. So initially, or before the collision, only the clay block has momentum. It's moving. Block 1 is not. After the collision, they're both moving. And we can find the common velocity of those two moving after the collision. Now, after the collision occurs, the spring is then compressed. So that is actually a conservation of energy problem. So I'm going to define a couple points here. Point A here, when there's no compression, and point B at maximum compression for energy. So I'm actually going to start an energy problem over here. The first part of the energy process is to find a reference line. So I'm going to make my reference line right here, where it all lies along. Okay. Step 2, I'm going to make a statement of energy. Energy at point A equals energy at point B, conservation of energy. And you should clearly make that statement when you're doing these problems so that the person grading your AP exam can see what points you're defining as the beginning and ending point. So here are my buckets. So I have kinetic at A, kinetic, potential due to gravity at A, potential due to spring at A, kinetic at B, UGB, and spring at B. So at point A, this clay block mass is moving, so we have kinetic energy. It's on the reference line, so there's no potential due to gravity. The spring is not yet compressed. At point B, it's not moving. It's at maximum compression. It's still on the reference line, but the spring is compressed. So we can write a conservation of energy equation. And if you recall, this is 1/2 kx squared, so we can solve for that distance x that it's compressed, is what we're interested in. So we have both the conservation of momentum and conservation of energy problem. Let me go back to one more detail I want to talk about for the conservation of momentum. The constraint or the condition that needs to be met for conservation of momentum is that there's no net external force acting on the system. However, if you look here, the spring is attached to block 1 at the time of collision. So that seems to violate the condition for the law of conservation of momentum. However, in the problem statement, it says that the collision occurs before the spring is significantly compressed. In other words, this collision happens so quickly that the spring doesn't have time to compress. Most collisions happen on the millisecond or microsecond time frame, so given that time, there's no compression here, and therefore no force applied by the spring. If this were a lengthy collision, it happened over a second or two, and this spring were to compress, then there would be a net external force, and then we could not use the law of conservation of momentum. But because of the short time frame of the collision, because it says that the collision occurs before the spring is significantly compressed, we can use the law of conservation of momentum.